Okay, let's turn over and look at the second page on this. There's a lot less on this page than it actually appears. For example, right here, this should be an irreversible expansion against a constant external pressure. Okay. The first law is still du equals dq plus dw. Neither the q nor the w are going to go to 0, so there's really no impact here. The q, dq, is going to be dq sub p, and that, of course, at a constant pressure is equal to the dH, and that will be n cp dt. And so you can integrate that, therefore, and the q will be equal to the delta H will be equal to n cp delta T. The work is against a constant external pressure, so it is, and it's irreversible. So dW is always equal to a minus p dV. However, the p is constant, so when I integrate it, my work is going to be equal to a minus p external delta V. My external pressure is the same as the P final of the gas. My change in volume will be, say that's in liters, and this is atmosphere. The way you get liter atmosphere product units to be the same as joules is you multiply by the 101.3 joule per liter atmosphere conversion factor, and the 101.3 comes from the ratio of the two values for R. Delta U then is just going to be equal to whatever you got for the Q plus W. So that'll be equal to your NCP delta T plus your minus P external delta V. Your delta H is always equal to a U plus PV, and so my delta H is equal to my delta U plus my P delta V. Delta T, you can find out what your T2 is. I'm just going to look back and show you where we've done this already. Use your ideal gas equation of state on each state for all of this space, and so you have P1 V1 over N1 T1 is equal to the gas constant R is equal to P2 V2 over N2 T2. Use that equation for one state or between both of them to determine any one of these unknowns and therefore the sign of the change. Okay? For a free expansion, that's against a vacuum. That's also irreversible, but it's working against a constant external pressure of 0. And so work is 0 in this case. And there's no Q exchanged because there's no change in temperature, there's no change in enthalpy, there's no Q, and the impact here is that du is equal to, well, 0. The delta V is greater than 0 because it's expanding into a bigger space, and so there'll probably be a pressure drop of the gas, but it's working against a vacuum, so really all it's doing is expanding into the available volume. So the P of the gas, the pressure of the gas, that depends on the particular problem, so why don't we just leave that one right now. But all that's happening here is that there's no exchange of energy. It doesn't cost any energy to expand into a vacuum for this ideal gas because there are no forces of attraction between the particles, and so they can expand their volume without an expenditure of energy. When we have a chemical reaction product, like for example, say 2A solid reacts with B, and it could be, we'll make it heterogeneous. There's no gas over here, but it makes a product gas. So that gas volume in initial is 0, and the volume final is the volume associated with PV and RT, which would be nRT over P. And so if this is being done on the bench at a constant pressure of 1 atmosphere, that's what that pressure is. So that when the gas is evolved from a chemical reaction, it takes the pressure of the room atmosphere. And the number of moles will be determined by a balanced chemical equation. R is your gas constant, and temperature is the temperature of the room, the bench, or of the reaction. And so this is very straightforward. The work associated with that, it is irreversible. And so my work is a minus P delta V, where that pressure is the 1 atmosphere that it's pushing back if it's happening on the bench. So let's say it's a constant external pressure, becomes the P final of the gas. And the delta V is V final minus V initial, but that V initial is equal to 0, and so it's really equal to the V final of the gas, which is nRT over P. So if you look carefully, it's P times nRT over P, so the work is really just equal to nRT. Delta H, well, it's the delta H of the reaction. There shouldn't be any change in temperature because it's a constant temperature reaction that's also done at a constant pressure. And the change in volume of the gas is basically just equal to V final because V initial is before the gas is even existing. And then if we do it in a finite number of steps, there's another video that shows how the work of this is done. We have pressure, volume, and remember we are initial and we drop the pressure and then it expands. So then in one step we have this area under the curve, and the work is always equal to a minus P external delta V. So whatever that external pressure is that it's working against, and the change in volume. So if you do it for 2 steps, it would be the initial pressure and the initial change in volume plus, and then a minus P delta V for the second step. But it's always irreversible, and it's like this. You would have to know more information to find out what Q is in the question, and then delta U would be the sum of these two. So it's Q plus W. There is a Q, it's not done adiabatically, so there is a Q. And the delta H is again equal to the delta U plus the delta of the PV. And it depends if it's done isothermal or not. It's usual, we usually do it isothermally. The delta V, it's an expansion, so it's going to be greater than 0. And it's against a constant pressure. And an irreversible expansion, well, we've just given you 3 examples, so it could be any one of these. Okay? So I'm going to do a different video for this one.